John, right? Okay, I'm gonna get started because everybody's late today. Chapter 19 homework is due on the 24th. Chapter 20 homework is due on the 31st. The chapter 19 quiz will be today in SI. The chapter 20 quiz will be next week on the 29th. And the exam on chapters 15, 19, and 20 will be on the 3rd, which is the Monday of the week after next. This is all on the schedule, so we're going to start chapter 20, atmospheric effect. We need to get through it. So we'll go over the 3 essentials of the Bergeron process and how it relates to the formation of precipitation. We'll talk about the different forms of precipitation, including rain, snow, hail, sleet, dew, and fog. We'll describe air masses based on their temperature and moisture content. We'll talk about the distinctions between warm and cold fronts. We'll describe the different types of lightning discharges and indicate which is the most dangerous. We'll talk about how you can estimate the distance to a thunderstorm using the distance equation, distance equals velocity times time, where velocity is equal to 1/3 of a kilometer per second or 1/5 of a mile per second. We'll differentiate among an ice storm, a snowstorm, and a blizzard. We'll describe the basis of wind chill. We'll talk about the formation of a tornado. We'll talk about the formation of a hurricane. We'll talk about air pollution. We'll differentiate between climate and weather. And we'll describe the effects of carbon dioxide and methane pollution on climate. So, the lower atmosphere that we live in, the troposphere, is dynamic. It results in frequent weather changes, and the movements and interactions of large air masses bring variations to our weather. Large air masses can move thousands of miles and influence a region for a considerable time period. So the general movement of air masses depends largely on the global circulation structure of the Earth, which we talked about in last chapter, but it can be affected by the more local effects. Now, condensation is the process of water vapor turning into liquid or solid. And in most situations, condensation occurs within an air mass when the dew point temperature is reached. In some cases, water vapor can be cooled below the dew point without condensation occurring. This happens when there is a lack of nuclei for condensation to occur around. And in this situation, the air mass is said to be supersaturated or supercooled. Water droplets don't form randomly, but they form around microscopic foreign particles called hygroscopic nuclei that are present in the air. And hygroscopic nuclei could be things like dust, smoke, soot, salt, other small airborne particles. And since droplets form around these hygroscopic nuclei, condensation provides a mechanism that cleans the atmosphere. So condensation occurs around crud in the atmosphere, and that then falls as rain eventually. And so you get that material cleaned out of the atmosphere. And if the proper type and size of airborne particles aren't present, condensation may not occur or will be delayed, retarded. So when condensation does occur, these tiny droplets are formed in updrafts and are easily suspended as a cloud. So when condensation occurs most of the time, it's cloud. You see the cloud, happy cloud. For precipitation, for the water to actually fall from the sky onto your head, this requires some process that causes larger droplets to form. Small droplets in a cloud will just stay up there as a cloud. But if larger droplets form, they will fall. 2 processes are thought to be responsible for this formation of large drops. And they occur in different conditions. So they're how we get rain in different conditions. They are collision coalescence or coalescence and the Bergeron process. Our rain here is primarily driven by the Bergeron process. Most rain over continents and things like that especially further north, is the Bergeron process. So coalescence is what happens in warmer situations. Bergeron process requires cold. So coalescence is the simpler of these two processes. It's the formation of larger droplets by the collision of small droplets. You have some drops collide and merge, and eventually they start to fall. And as they fall, they sweep up other droplets and get bigger. Eventually they get bigger, then they will break into smaller pieces, and those will fall and start expanding as well. And the process of coalescence is most efficient when the original droplets are relatively large. So starting with large droplets around 100 micrometers enhances this coalescence process by limiting the number of collisions necessary to form raindrops. Now the other process is called the Bergeron process. This is a process by which larger ice crystals form at the expense of smaller water droplets. So it requires cold. This is named after the Swedish meteorologist that proposed it, and is thought to be the most important precipitation process. Remember, the upper atmosphere is generally always pretty cold, so you can get the temperatures required for the Bergeron process even, say, during the summer. So the Bergeron process involves three essential components: ice crystals in the upper portion of the cloud, supercooled vapor in the lower portion of the cloud, and a mixing or agitation that brings the ice crystals in contact with the supercooled vapor. Basically, what happens is that at a certain temperature range, below freezing, water is more attracted to ice than it is to water vapor is more likely to form ice than it is to form liquid water. And that means if you have ice crystals and liquid water, the ice crystals will suck up the water vapor, making there be less water vapor around. The little water droplets will then evaporate, and that water will continue to be sucked onto the ice. So the ice crystals serve as condensation nuclei. They grow larger from the vapor condensing on them. They form snowflakes. So here is the Bergeron process, how it works.
Hi, class.
Oops. And of course, I forgot to set the audio settings right. Oops.
Hi, class. I wanted to talk a little bit about the processes that form precipitation in clouds. And the two main processes that we're going to look at are the Bergeron process and the collision coalescence process. So let's start first with the Bergeron process. And the key here is that this process occurs in the higher, colder parts of clouds in the mid-latitudes over continents and over oceans as well. And so the key here is that they have to be cold, so it has to be clouds that are tall enough that you have a high part that's very cold. And in that cold part, there's the coexistence of water vapor, liquid water droplets, and ice crystals. So water is existing in all three phases: solid, liquid, and gas. And what's happening in the Bergeron process is that the ice crystals are growing faster than the droplets. So the key here is that precipitation is formed in the form of ice crystals. Now, when it finally reaches the ground, it can be rain because it may have melted by then. But the formation of the precipitation is in the form of ice. And there's a net movement of water vapor from droplets to ice crystals. So the reason that this happens is that the saturation vapor pressure relative to ice is lower than it is for water. So for example, if we're at a temperature of -20 degrees C, our saturation vapor pressure for ice is only 1, where it's about 1.2 for water. So if we take an air mass and we cool it, it's going to hit saturation next to the ice crystal sooner than it is going to hit it next to the water droplet. And so to illustrate the Bergeron process, we're going to look at two chambers, one that is filled with ice, so this light blue rectangle here is ice, and this dark blue rectangle here represents water. And these are two chambers that are separate, but they're both sealed. And they're both at saturation, so the little dots represent water molecules in the vapor form. And you can see that the vapor pressure over the water at saturation is much higher than it is over ice. And notice that it says the temperature is less than 0 degrees C. Now, water can actually be supercooled and still stay in its vapor form. And we'll talk a little bit more about how and why that happens. So what we're going to do now is open this barrier and see what happens to the water vapor above the ice and above the water. So we open the barrier, and what's going to happen is the water vapor molecules are going to move from where there's a high concentration to where there's a low concentration. So we have a net movement from high concentration to low concentration. We have a gradient, a concentration gradient here. And so we can see the water vapor molecules move over here. So now we're going to have a net movement into ice formation via the process of deposition. And so the ice crystals are going to get bigger. The droplets are going to get smaller. There's a net movement of water molecules out of the liquid water droplets. So essentially we're having evaporation of the droplets and deposition or growth of the ice crystals. So we've got a net water transport from the droplets to the ice crystals and an increase in the size of the ice crystals. So to illustrate the Bergeron process, we have this high vapor pressure around the droplets, and we have this net movement to the low vapor pressure region around the ice, and so the ice crystal grows and the water droplets shrink. So the key here is that the Bergeron process has to happen in really tall clouds. So notice where most of this cloud height, and what kind of cloud is this? It's got that anvil top. This is a cumulonimbus cloud, and it's over land. And so most of the cloud is at a height where the temperatures are below freezing. And so those droplets are getting pushed up by uplift in the cloud. We have the Bergeron process, which is causing the growth of the ice crystals that look like snowflakes here. And then as they fall, they pass this freezing point, they turn back to liquid, and it falls as rain. And this is how a lot of our precipitation here in Colorado is formed, even when it forms as rain, when we have these tall cumulonimbus thunderstorm clouds. And the same thing can happen over the ocean. You can see we have the formation of the ice crystals here and then falling down and passing the freezing point and then falling as liquid water. So the difference when we don't have those tall, cold cloud tops is that we have the water staying more as liquid. And this also happens in the regions of the tall clouds that are below the freezing level. So in the warm part of those clouds, the water still is liquid, and what happens is these tiny cloud droplets bump into each other and they coalesce into larger droplets. Now they get so big that they'll fall apart, they'll break apart as they fall, and 5 millimeters is the maximum size. So we start here with the cloud droplets colliding and coalescing into a big enough raindrop that can actually fall, and it might get too big, and because of friction and air resistance, it might break apart into smaller drops. And the coalescence occurs partly because of the electrostatic charge of the different water droplets. If we just relied on condensation growth, so this is droplet radius with time, if we just relied on condensation growth, those droplets wouldn't get big enough. And so we need that collision and coalescence process to make the droplets grow big enough that they can fall to the ground without evaporating before they hit the ground. So to compare what we have going on, this is our continental and some oceanic cold rain process where we have these tall clouds, really high vertical extent above the level at which the temperature is freezing, and so a lot of the formation is occurring as ice crystals. And if we have clouds that are lower down, where a lot of the cloud is below the level at which freezing temperatures occur, then we have the collision coalescence process becoming.
So the Bergeron process, its mixing of ice crystals and super cold water vapor leads to the production of large ice crystals. These large ice crystals then melt into large droplets of water as they fall in the lower portion of the cloud, coalesce, and fall as precipitation. That's sort of a rough outline. The main idea in the Bergeron process is that basically ice pulls water vapor away from water droplets, and the ice crystals can get really big enough to fall. So modern rainmaking techniques are based on the essentials of the Bergeron process. In one method, very small silver iodide crystals are produced to serve as ice crystal nuclei, because silver iodide crystals have the same, roughly the same crystal structure as ice, so it's very easy for ice to grow on them. Another method, in fact, the first method, involved dumping dry ice pellets to quickly cool the cloud and trigger the conversion of supercooled droplets into ice crystals. So the dry ice sublimes, turns from a solid into gas, resulting in rapid cooling of the cloud that triggers the formation of ice crystals, which and cools the area, so it sort of supercharges the Bergeron process and speeds up the start of rain. So precipitation occurs in the form of rain, snow, sleet, hail, dew, or fog. In the lower and middle latitudes, rain is the most common form of precipitation. If the dew point is below 0 degrees Celsius, snow will form. Snowflakes are hexagonal due to the hexagonal crystal structure of ice. Sleet falls directly from a cloud as ice pellets, or forms when rain freezes before it hits the ground, and as it falls through a cold near surface layer. So sleet is frozen raindrops. Snow formed as ice crystals in the cloud. Sleet, it was a raindrop that froze into a little pellet of ice. Hail are large pellets of ice that form from successive vertical descents and ascents within convection cells of thunderstorms. So hailstorms form as these pellets of ice get cycled up and down and build up layers of ice in each cycle. So if you cut a hailstone in half, it'll have concentric shells as it builds up layers. Dew forms when atmospheric water vapor condenses on various surfaces. So when the land cools quickly at night, water vapor will condense on available surfaces like grass blades. And if the dew point is below freezing, water vapor will change directly into ice crystals called frost in a process that's called deposition. Frost is not frozen dew. Frozen dew and frost look different. Frost will have that weird ferny structure. Frozen dew will look like little frozen water droplets. In general, the weather conditions at every given place depend largely on vast air masses that move across the country. So an air mass is a large body of air that takes on the physical characteristics that distinguish it from the surrounding air. Basically, an air mass picks up the properties of someplace it was for a while, and then when it moves, it keeps those properties. So it ends up different from its surroundings. The main physical characteristics that distinguish an air mass are temperature. Is it hot? Is it cold? And moisture content. Is it wet or is it dry? So when a large mass of air remains for some time over a particular region, so if you had a big mass of air sitting over the North Atlantic, let's say, it's going to be cold and wet. So it'll take but if you also had a large mass of air sitting over, the American Southwest for a long time, it's going to be warm and dry. So an air mass picks up the properties of the region from where it derives its characteristics. This is called the source region. And an air mass will eventually move from its source region and will bring along its physical characteristics. So air masses are classified according to the source, the surface of the source region, and the general latitude of their source regions. So the surface, you could have wet, maritime, it's from over the ocean, or dry, continental, it's from over land. And then the latitude, the coldest air masses are Arctic, then polar, then tropical, then equatorial. So Arctic air masses are super cold, polar air masses are cold, tropical air masses are warm, equatorial masses are very warm. And the global circulation patterns greatly influence the movement of air masses. The continental US is located within the conterminous US, is located within the westerlies, and hence the general movement of air masses is from west to east. Not working. Oh, you are loading. Just a second. I'm gonna unhide the slide because this seems broken.
This is incredible. Oh, it's in such good condition.
It's not gonna fit.
Oh, it's gonna fit.
Because there are large antiques in your area, there are drivers in your area.
It's nice.
Uber.
Air masses.
Yeah.
An air mass is a volume of air that's defined by two things, its temperature and its water vapor content. Air masses can be huge. They may cover hundreds or even thousands of square miles, and they're going to take on the characteristics of the land or ocean that is beneath them. That is to say, an air mass that sits over the ocean will tend to be a humid air mass, while one forming over the land will be more dry. Now, there are 5 major types of air masses that impact the weather in the continental United States and North America as a whole. The first one we're going to look at comes down from far northern Canada, near the Arctic Circle. This is called a continental Arctic air mass, abbreviated lowercase c, uppercase a. The fact that it formed over land makes it a dry air mass, and because it is so far from the equator, up near the North Pole, it's an extremely cold air mass. Ca air masses rarely make it all the way down to the United States, though they do have an impact on our weather. The more common cold air mass that affects us in the United States is a CP, or continental polar air mass. This sort of air mass is dry and cold, though not quite as cold as an Arctic air mass. These swoop down from Canada and have a major impact on the weather in the northeastern United States. We also have wet, cold air masses that affect the northwest portion of the United States. These are called MP, or maritime polar air masses. The word maritime tells you it formed over the ocean, making it a humid air mass, and of course polar refers to it being cold. We may also see maritime polar air masses moving onshore from the North Atlantic Ocean. Let's take a look at some of the warmer air masses that affect the United States, starting with the continental tropical, or CT, air masses that move northeastern from Mexico. These air masses are very dry and very hot, and have a major impact on the climates of Texas and Oklahoma. We also have maritime tropical, humid, hot air masses that affect the United States. The major source of these air masses is the Gulf of Mexico and the South Atlantic Ocean. So these are a look at the major air masses affecting the United States. Remember, the abbreviations and names for these air masses can be found in your reference tables. And you should pay careful attention to the CP air masses, which move south from Canada, and the MT air masses that move north from the Gulf of Mexico, as those air masses interact in the eastern part of the country to create thunderstorms in the springtime and have a major impact on the climate for New York State.
So here are some examples of various air masses that affect North America. We have maritime polar, maritime tropical, continental polar, and continental Arctic. And also maritime Arctic up here affecting, Alaska. Oh, that was the wrong button. So The boundary between two air masses is called a front. This is describing it as, the analogy is a battle. They're using military terms. A cold front is the boundary of a cold air mass advancing over a warmer surface. So when the cold air is moving over warmer air, that's a cold front. And the opposite is a warm front, when warm air is advancing over a colder surface. Now what always happens is the warm air ends up on top of the cold air, but if it's a cold front, the warm air gets pushed up very rapidly. Because the cold air comes in and basically hits it like a bulldozer. But if it's a warm front, the warm air blowing over the cold air rises over it and sort of settles over it, so the change happens much less rapidly. So here is a video about cold and warm fronts.
This animation is going to describe how precipitation happens at what are called cold fronts and warm fronts. These are weather systems that develop wherever masses of cold air collide with masses of warm air. And the name actually comes from war, where armies would meet along a battle line called a front. And one way to think about the difference between cold fronts and warm fronts is to think about which mass of air is going to win the battle. So we'll start with a cold front. This is a situation that happens where cold air moves in like a big wedge underneath warm air. Cold air is always heavier than warm air, and so it's denser, and it's going to tend to slide under the warm air and push the warm air upward. Anytime you have air rising upward, it's going to expand and cool and lose its ability to hold moisture, and this will give you a band of clouds and precipitation along a cold front. On weather maps, if you watch the weather on the news, you can see cold fronts marked by lines of blue teeth that point in the direction the cold air is moving. Along cold fronts, you typically have very intense local thunderstorms and rainstorms. So it might pour rain for a short time, but then quickly, usually within an hour or so, the front will have moved on. So a cold front is where the cold air pushes underneath the warm air, and you have high rainfall and usually intense thunderstorms. Now, the warm front has in common a couple of things with the cold front. One is that the warm air still goes up on top of the cold air, but in this case the warm air is actually pushing the cold air out of the picture. So the warm air is winning, and that's how you can remember it. It's a warm front. The warm air pushes against the cold air, squeezing it out, like imagine squeezing a watermelon seed between your fingers. It kind of squeezes out, right? And as the air pushes, it also rises up over the cold air. Rising air, again, loses its ability to hold moisture, and you tend to get clouds and rain. On long warm fronts, you typically have more mild, more mellow, more spread out rainstorms rather than really local intense thunderstorms. And if you're looking at the weather on the news, they mark warm fronts on maps with red half moons that point in the direction that the warm air is pushing the cold air. So that's cold fronts and warm fronts, major precipitation belts in many places on the Earth.
So cold fronts generally form a sharp, steep boundary where the lighter warm air gets displaced upwards. They're accompanied by more violent and sudden changes in weather. Those short, really intense thunderstorms, that's a cold front. Warm fronts form a more gradual boundary because it's more difficult for the lighter warm air to displace the denser cold air. So instead of like hitting the warm air like a bulldozer and pushing it up and out of the way, the warm air has to squeeze the cold air out like toothpaste in a tube. That spreads the rising warm air out. It spreads out the precipitation. You get longer, less severe precipitation. So there's standard symbols. Cold fronts are expressed with pointy teeth, commonly colored blue. Warm fronts are expressed with half circles, commonly colored red. If you have a cold front overtaking an active warm front, you get what's called an included front, which has both teeth and half circles. And if you have a stationary front that's not moving, neither cold nor warm is winning, you get this teeth on one side and half moons on the other. And the direction that the front is moving is indicated by the side of the line with the symbols. So all of these three would be moving upwards and stationary fronts aren't moving. So here's an example of a typical weather map. We have colors to represent temperature, and temperature is marked on this. We have a couple of fronts. We have a cold front here moving southeast. We have a warm front here moving mostly west. I mean southwest. This is moving mostly west. There's another warm front here moving mostly south. Another cold front here moving mostly south, and a warm front here moving sort of north. And we have areas of precipitation. We have snow, snow up here, showers along here, flurries up here. We have showers along here. I don't see any thunderstorms on here. So another thing that happens is you get changes in pressure. Air masses that move across the country will give rise to cyclonic low pressure and anticyclonic high pressure regions. Low pressure systems carry rising air currents, clouds, and possible precipitation. Low pressures are generally associated with poor weather. High pressure systems carry falling air currents, clear skies, and fair weather. Highs are generally associated with good weather. And the positions of highs and lows are monitored, and they're often marked with L's and H's on a weather map. So here is a short video about high and low pressure systems.
Hi everyone, I'm Marissa from the National Weather Service in El Paso, Texas. Today on Weather Basics, I want to talk about high and low pressure. Air pressure can tell us what kind of weather to expect. A sudden drop in air pressure usually brings stormy weather. We call this drop in pressure low pressure. Low pressure is usually represented by a red L on weather maps. At the surface, moist air comes together or converges, then rises to create stormy weather. Surface winds in the northern hemisphere blow counterclockwise around a low pressure system. A good way to remember what kind of weather low pressure creates is to remember that low pressure generally creates lousy weather, like rain, snow, and wind. A rise in air pressure means we can expect good weather. We call this rise in air pressure high pressure. High pressure is usually represented by a blue H on weather maps. In the atmosphere, dry air sinks, then diverges or separates to create nice weather. Surface winds in the northern hemisphere blow clockwise around a high pressure system. A good way to remember what kind of weather high pressure systems creates is to remember that high pressure creates happy weather that is sunny, warm, and calm. So high pressure, happy weather. A way to further investigate high and low pressure is to build a homemade barometer like we've done here and track air pressure changes in your area. Here's our homemade barometer. All you need is a piece of paper, a straw, a balloon, some rubber bands, and a glass jar. As the weather changes, so will the height of the balloon, and the straw will rise and fall against the line on the card. If the air pressure rises, the balloon is pressed down and the end of the straw is pushed up. So if your straw is above the line on your card, then the air pressure is higher than on the day you made your barometer, and you will have fairer weather. If the pointer is lower than the mark you made on the card, then the air pressure is lower than on the day you made your barometer, and your weather will be worse. If you would like to make a homemade barometer like we did here, or for more information, head on over to the Weather Basics website linked below. Thank you for joining me today on Weather Basics, all about high and low pressure. See you next time.
So a storm is an atmospheric disturbance that can develop within a single air mass or may develop along the boundary between air masses. And storms can be divided into two types: local storms and tropical storms. Local storms are what we generally encounter: rainstorms, thunderstorms, ice storms, snowstorms, and tornadoes. Tropical storms are those massive storms that are like hurricanes and cyclones and whatever the heck Superstorm Sandy was. because we're so far inland, we don't really get tropical storms. Because tropical storms are fed by warm water, so we don't actually encounter them very often. So, some local storms. A rainstorm is a heavy localized downpour. 1 to 3 inches per hour is common. A thunderstorm is a rainstorm with lightning, thunder, and sometimes hail. So lightning is a discharge of electrical energy, and it occurs in a thundercloud when there is a separation of charges due to the breakup and movement of water droplets. Basically, as water droplets rub against each other and move around, there could be a separation of charges. And as the charges separate, an electric potential arises. So you have positive charges on one end. I think what you get is that negative charges go up and positive charges go down, but I might have it backwards. But you have opposite charges at opposite ends of the cloud. So lightning is a way to correct that by moving the charge around. And it can occur in several ways. It can occur entirely within a cloud. You could have just lightning flows within the cloud. This is called an intercloud lightning. This is some of the more common types of lightning. Goes from that positive charge at one end of the cloud to the negative charge at the other, or vice versa. Between two clouds, cloud to cloud. Between a cloud and the ground, which is the most dangerous to humans and properties, because all these are up in the air. And then lastly, between a cloud and air, what's called an air discharge. It just sort of discharges out into the air, it dissipates. On average, about 200 people are killed each year by lightning. And some places have more lightning than others. It has to do with the weather conditions to create the right kind of clouds. There are places where there are lightning storms almost every day. Now, thunder is the sound generated by lightning. Because lightning is this huge, massive spark. It superheats the air. You get a compression wave by that sudden release of electrical energy. If the lightning's very close, 100 meters or less, you'll hear a single loud clap. If the lightning's at a distance of 1 kilometer or more, the thunder consists of more of a rumbling sound. And thunder can't be heard more than about 25 kilometers from the lightning. And you can measure the time difference between seeing the lightning and hearing the thunder to figure out how far away the storm is. Yes. So here we go. Come on.
The image is unmistakable. Lightning is one of the most incredible natural phenomenons, and one that scientists are still learning about. It's a common occurrence during summer when the heat of the day is broken by strokes of lightning. Worldwide, it's estimated lightning occurs 50 to 100 times a second. The greatest concentrations of lightning strikes are in Central Africa, the Himalayas, and South America. Lightning is often seen flashing between storm clouds in the earth. The bursts of light are pure electricity. Scientists don't fully agree on what actually causes the electrical charge to be dispersed, but it is generally thought that lightning often occurs within the downdrafts and updrafts of thunderstorms. Lighter particles moving toward the top of clouds become positively charged, while heavier particles heading toward the bottom become negatively charged. When the positive and negative charges grow large enough, lightning is released between these regions. Most of the lightning takes place within the cloud, but some strikes the earth in bold flashes. In these cases, the charge escapes the cloud, making a branching path that reaches for the ground. The energy of the lightning strike contains hundreds of millions of volts and lasts only a fraction of a second. What seems to be a single flash is actually a series of return strokes of electrical energy reaching back up into the clouds. The path reaches temperatures of around 50,000 degrees Fahrenheit. This extreme heat creates the booming thunderclap as excessive pressure within the lightning path expands at supersonic rates on return strokes. In the U.S., lightning occurs most often in Florida. Its hot, moist climate is perfect for creating thunderclouds, which produce lightning. But lightning is a deadly natural phenomenon, taking nearly 100 lives a year on average in the U.S., more than hurricanes or tornadoes. During electrical storms, experts warn that people should seek shelter inside a building or hard-topped automobiles, and if caught in the open, avoid high ground and isolated trees. Lightning is a powerful force of nature and one to be cautious of.
Yeah, if you're out and about and not able to get inside a building, most buildings have, protections against lightning, and they're pretty good at dealing with it. Being inside a car is one of the safest places to be. Because if the car gets hit by lightning, the electricity will travel around the outside of the car and go to the ground, and it won't hit you. So lightning flash travels at the speed of light, which is 300,000 kilometers per second. So it's on the scales of the Earth, it's more or less instant. It's very, very, very fast. But thunder is sound and only travels at like legitimately a third of a kilometer per second. So like a millionth of the speed of light. So you can assume, for calculating roughly, that you can assume the lightning flash took 0 time to get to you and calculate just based on the speed of sound, which is about a third of a kilometer per second or a fifth of a mile per second. The lightning flash is seen essentially immediately, but there's a delay in hearing the sound of the thunder, and the difference in time between the lightning and hearing the thunder can be used to determine the distance. So basically, if you see a lightning flash and then you count how many seconds it takes for you to hear it, for every 3 seconds, that's a kilometer. Every 5 seconds is a mile, because kilometers are shorter than miles. So suppose some campers notice approaching thunderstorm, lightning is seen, and the thunder is heard 5 seconds later. About how far away is it in kilometers and miles? So 5 seconds, the velocity is a third of a kilometer per second or a fifth of a mile per second. So a third of a kilometer per second times 5 seconds is 1.6 kilometers. A fifth of a mile per second times 5 seconds is 1 mile. You just divide the time by 3 to find kilometers or 5 to find miles. So here are some other examples of local storms. An ice storm occurs when the temperature of the Earth's surface is below freezing while it's raining. So the rain will freeze on contact, coating everything in ice. And the weight of the ice on trees and power lines can cause significant damage because it doesn't fall off. It sticks. A snowstorm is an appreciable accumulation of snow. If a snowstorm also has high winds and low temperatures, it's called a blizzard. So you need to have a lot of snow and high winds and low temperatures for it to be a blizzard. And the most violent of storms is a tornado. So tornadoes form when warm, humid air collide with cold, dry air, which basically the center of the US is just about perfect for, because there's very little between the Gulf of Mexico and northern Canada. So cold, dry air comes down from northern Canada, warm, moist air comes up from the Gulf of Mexico, they hit each other, and you get Tornado Alley. In fact, Tornado Alley in the center of the US is the place where tornadoes are the most common in the world. The other place where they're, the number 2 place is in the center of Australia, where similar effects can happen. So, although tornadoes may not be as large as other storms, this tornado is so concentrated that it has great destructive potential. They can basically just, level an area that when they touch down and pass through. It's so violent. So I remember at the camp I worked at, there was just, there was an area of forest that had just been basically erased. There was now a big clearing because a tornado touched down. And the tornadoes are most common in the US and Australia, specifically in the US. Most tornadoes in the US occur between the Rockies and the Appalachians. And April, May, and June are the peak times for tornadoes in the US. And we are in that tornado zone. We live in the tornado zone. Tornadoes are a risk we have to worry about. So notifications about tornadoes, a tornado watch is issued when the atmospheric conditions indicate that tornadoes may form, and a tornado warning issues when a tornado has actually been sighted or indicated on radar. And the unfortunate thing is that tornadoes are a complicated enough phenomenon that happen for a short enough time, they're extremely hard to predict. So it's very hard to work out tornadoes. And we don't have a full understanding of exactly how they work. But here's roughly how they form.
The average tornado has a lifespan of just a few minutes, but that's more than enough time for one of the world's most destructive weather events to form. The most extreme tornadoes can last for hours, span miles in diameter, and whip up wind speeds over 300 miles per hour. To prepare for these dangerous weather events, meteorologists have spent decades researching how tornadoes come to be. Tornadoes develop out of what's called a supercell thunderstorm, which is a normal thunderstorm with a persistent rotating updraft at its core. This rotating updraft grows into something called a vortex, a spinning column of air at the center of the storm. As a supercell grows in size, the vortex in the middle will begin to tilt, pulling warm air and moisture upward and pushing cold, dry air down toward the ground. The updraft of warm air causes the vortex to swell with water vapor, creating a spiraling funnel cloud. The cool downdraft begins to battle the funnel cloud's upward spiral, focusing the cloud into a smaller area and increasing its speed. With enough pressure and weight from the battling hot and cool air, the funnel cloud is forced down to the ground and a tornado is born. Modern technologies like Doppler radar allow meteorologists to track the moisture and pressure in the air, allowing them to notice the early stages of a tornado forming before the funnel cloud is even visible. And with every second of early warning, more damage can be prevented and more lives saved.
So the Fujita tornado scale was developed in 1971 by T.T. Fujita of the University of Chicago. And this is the enhanced Fujita tornado scale. Tornadoes are rated with EF from 0 to 5. So an EF 0 has a wind speed of 65 to 85 miles per hour. There's some damage to roofs and chimneys, branches are broken off trees, shallow-rooted trees get pushed over, signboards are damaged, moderate damage. EF1 is 86 to 110 miles per hour. You get roofs severely stripped, mobile homes overturned or badly damaged, windows and other glass broken, considerable damage. EF2 is 111 to 135 miles per hour. Roofs torn off of frame houses, mobile homes demolished, large trees snapped or uprooted, light object missiles generated, cars lifted off the ground, severe damage. EF3 is 136 to 165 miles per hour. Entire stories of well-constructed houses are destroyed, trains are overturned, trees are debarked, heavy cars are lifted off the ground and thrown, and devastating damage. EF4 is 166 to 200 miles per hour. Well-constructed houses and whole frame houses are completely leveled. Cars are thrown and small missiles are generated. This is total destruction. And in EF5, it's over 200 miles per hour. Strong frame houses are lifted off of foundations and swept away. automobile-sized missiles fly through the air in excess of 300 feet. Steel reinforced concrete structures get badly damaged, and this is incredible phenomenon will occur. But these are very rare. Generally, you get much smaller tornadoes. And here is the average number of tornadoes per year. As you can see, we're in a pretty hot region in the 5 zone, maybe 3 to 5 zone. I mean, the highest is down over here in Oklahoma, but this whole region is Tornado Alley. Gets lots of tornadoes because the warm, moist air from the Gulf of Mexico hitting the cold, dry air from Canada. Oh, okay. I guess I heard a little more than I needed. I will continue on a little bit. So, a tropical storm is a massive weather disturbance that forms over tropical oceanic regions. Tropical storms are classified as hurricanes once their wind speed exceeds 119 kilometers per hour, 74 miles per hour. They're hurricanes in the Atlantic. There's like weird naming conventions for tropical storms. But like they have different names in different regions. They're like cyclones in the, they're typhoons in the Pacific, there's cyclones in the Indian Ocean, but they're all the same thing. So we're just going to call them hurricanes from now on because that's what generally hits the US. Because most of the tropical storms in the Pacific tend to be towards the western side of the Pacific, hitting mostly Asia. But there are a bunch of different names. So hurricanes. The diameters of hurricanes range from about 480 to 960 kilometers, and their wind speeds can range from 119 to 320 kilometers per hour. They are getting bigger and stronger recently because of the warming of the earth. So graphs show the average tropical storm activity by month and region. So you can see there are hurricanes over here hitting the US, typhoons over in the Pacific, cyclones in the Indian Ocean, and if they're hitting Australia, they get called Willy Willies. So in the Atlantic Ocean, they're known as hurricanes. In the Indian Ocean, they're known as cyclones, and they're known as typhoons in Southeast Asia, in the Pacific. So in Japan and Southeast Asia, they're typhoons. And China. So they have different names in different parts of the world, but they're all the same things. They're cyclonic storms that are over 118 kilometers per hour in wind speed. And these show the average tropical storm activity by month and region. So this is the number of hurricanes in green, and the purple is the number of hurricanes making landfall. And hurricane season peaks in about August, September. So peaks in August, September, starts to peter off in October. So late summer, early fall is the peak of hurricane season. So hurricanes occur over tropical ocean areas where the sun heats enormous masses of moist air, which is why they tend to occur, in late summer, early fall, at the when the surface of the ocean is the warmest. And as this moist air gets heated, you get a low pressure cell formed with an accompanying rising air pattern and counterclockwise cyclonic rotation in the northern hemisphere. And as the moisture in the air rises, it condenses and releases its latent heat, feeding the hurricane. So hurricanes are fed by the warm water underneath them. So the latent heat of condensation and solar energy are the chief sources of the energy of a hurricane. The main feeding factor, the main source of energy for a hurricane is that warm water underneath it. That warm evaporating water feeding it. And that's why they peter out once they hit land. So here's a video about hurricanes.
Violent winds, driving rain, killer waves. These are the hallmarks of a hurricane. Also called cyclones or typhoons, hurricanes are giant storms prowling the world's tropical seas. An average hurricane releases as much energy in a day as the explosion of 500,000 small atomic bombs. Hurricanes form in the summer and fall when the sun heats vast stretches of tropical ocean to over 82 degrees. Warm, moist air rises over these hot spots, creating thunderstorms. Upper-level winds and surface winds then come together, forming a circular pattern of clouds known as a tropical depression. When the winds exceed 39 miles per hour, a tropical storm has developed. When the winds reach 74 miles per hour, a hurricane is officially born. Inside the storm, bands of rain up to 300 miles long meet in the eye wall, the most violent section. Here, winds of up to 200 miles per hour spiral upward. Within the center of the hurricane, downdrafts of dry air create a strangely calm area called the eye. Fully formed, a hurricane may stretch over 500 miles in diameter. That's a storm nearly the size of Texas and reach a height of 9 miles. Most of these storms spin out over the open sea, but in an average year, 2 or 3 will strike the mainland of North America. And when they do, the damage can be catastrophic. Most dangerous is the storm surge, a wall of water that sweeps across the coastline where a hurricane makes landfall. About 45,000 people were killed by hurricanes in the 20th century, including some 15,000 in the United States. Hurricanes are also costly in dollars. 1992's Hurricane Andrew was the most expensive natural disaster in U.S. history, causing more than $25 billion worth of damage. Scientists are searching for better ways to predict the path of a hurricane. Special planes called hurricane hunters fly directly into these monster storms and drop sensors to measure wind speed, temperature, and air pressure, providing vital clues to the hurricane's direction. New 3D models are also helping scientists understand this awesome force of nature and provide quicker and more accurate warnings to anyone unlucky enough to be caught in its path.
So, global warming is warming the ocean, and that is leading to bigger, more violent hurricanes. So I don't think the number of tropical storms has actually increased that much, but the number of seriously damaging hurricanes and the severity of all the hurricanes has increased, which means the number of hurricanes that are like a big problem has increased. And right now that's extra bad because our ability to deal with hurricanes is currently decreased because of politics. But you know, this is Hurricane Katrina from 2005. You can see the eye, which is very clear, and then we have the storm on either side. So hurricanes are getting bigger and more violent. In fact, there's been discussion about adding a step to the hurricane rating scale. So the hurricane destruction and death, while hurricane winds can do enormous damage, the greatest cause of death is drowning, because you get massive flooding and you get this storm surge. So most hurricane-related deaths, about 9 out of 10, are attributed to the storm surge. So as this hurricane comes forward, it basically pushes water in front of it. This great dome of water that accompanies the storm as it makes landfall. And you get this surge of water and massive sudden flooding that is that's caused by the hurricane winds and the low pressure of the storm. And this is incredibly damaging and is the biggest cause of deaths. So the storm surge can bring huge waves and storm tide. They can be more than 5 meters above normal. And in many cases, the storm surge comes suddenly, floods these broad coastal lowlands, and traps people from leaving the area. And of course, these hurricanes are accompanied with massive amounts of rainfall, so you get horrible flooding from that as well. And so the Saffir-Simpson hurricane scale, which was developed in 1969, if wind category 1 hurricane, winds from 74 to 95 miles per hour, the damage is minimal. You have dangerous winds producing some damage. Low-lying coastal roads get flooded. You get minor pier damage, some power outages. Category 2, winds from 96 to 110 miles per hour. Significant damage to mobile homes. Large trees get blown over. Major roof damage to homes. Typically significant flooding. Moderate damage to home exteriors. Large areas of power outage. Evacuation of some shoreline residents. Category 3 is devastating. Now it's a major hurricane. Structural damage can occur to homes and small buildings. Large buildings can also sustain damage. Mobile homes are largely destroyed. Category 4 is catastrophic. Structural damage to nearby buildings, roof failure on many buildings, flooding and wind damage could extend far inland. Storm surge is generally over 13 feet and will lead to widespread flooding, but height can vary. And then category 5 is more than 155. All trees blown down, some buildings removed from their foundation, near total roof failure, flood damage to lower floors less than 15 feet above sea level. Devastating wind damage can extend far inland, especially if the system is quick moving. And the thing is, we're getting more category 5s and even extremely severe category 5s. There is some debate about creating a category 6. So the thing is, once hurricanes hit land, they rapidly diminish in strength because they no longer gain energy from the warm ocean water, and they're subjected to significant friction over the land. They get much weaker. Even so, the remnants of a hurricane can bring significant rainfall and flooding for hundreds of miles inland. Because flooding is the biggest problem with hurricanes. And then some nomenclature: a hurricane watch is issued for coastal areas when there's a threat of hurricane conditions within the next 24 to 36 hours. The nice thing about hurricanes is you can tell they're coming from a long way away. Their path is pretty easy to predict. They're these big, relatively slow-moving things. You can figure out when they're coming relatively far away. And then a hurricane warning is issued for areas where hurricane conditions are expected within 24 hours. And I think we're going to stop there at this second set of announcements. I have about 5 minutes left, but let me just check where we are in the slides. Yes, we're going to stop here. So you have a quiz today in SI, and I will see you all next week.